The next topic we learn in this chapter is the wave nature of light. So light travels through space as a wave, similar to the ocean wave. It does not travel at a straight line. Wavelength, frequency, and the speed of light, they are three properties of a wave. So wavelength or lambda is the distance the light wave travels in one cycle. But frequency is the number of wave cycles completed in each second. The relationship between wavelength and frequency is C equal lambda multiplied by the frequency, whereas C is the speed of light in vacuum with the value of 3 multiplied by 10 to the power of 8 meter per second. Because the product of wavelength and frequency is a constant, the wavelength and the frequency, they are interdependent quantity. This means that if one is specified, the other one can be determined. So look at the wavelength, how you define the wavelength. Like I said, a wavelength defined by from a grass to the next grass. And for the longer wavelength, it's a lower frequency, where the shorter wavelength have the higher frequency. You see here for 1 second, for the longer wavelength, you only see one wavelength. For the higher frequency, for the 1 second, you can see the 1, 2, 3 wavelengths. So they are inverse relationship. One increases, the other one decreases. So light is a continuous spectrum. It usually refers to a radiant energy that's visible to human eyes. And that visible spectrum is in a range of wavelength between 400 and 700 nanometer. Although the radiant energy that have wavelength lower than 400 nanometer and greater than 700 nanometer, but they cannot be seen by the human eyes. The complete radiant energy spectrum is an uninterrupted band, or we call it a continuous spectrum. So the radiant energy spectrum would include the many type of radiation, most of which they are not visible to human eyes. For example, like UV light, X-ray, gamma, or cosmic rays, they are not visible to human eyes. Likewise, microwaves, TV, or radio, they are not visible to human's eye. The energy and wavelength are related by this the formula that energy equal Planck constant multiplied by the frequency. Now, because frequency equals to a speed of light divided by wavelength, you can calculate energy for each light based on the wavelength. The higher wavelength, it means the lower the energy, and the lower wavelength, it means the higher energy. So for the 700 nanometer light, got lower energy than the 400 nanometer light. Emission light spectrum, you will observe them in the lab through the spectrum and not through the individual light shown here. How you obtain it? So when an electrical voltage is passed across a gas in a sealed tube, you will see it in the lab. From Wednesday lab, Mondays are seen it. A series of narrow band lines is seen. Now we don't see it in the lab. Like I said, we see the spectrum. For each of the line, you see a peak from the spectrum. So these lines are the emission light spectrum. The emission light spectrum for hydrogen gas shows 3 lines: the violet, the blue, green, and the red. Now, the emission light spectrum is unique for each element. For example, I show in the case of hydrogen, you can see the violet, the teal, and the red. For sodium, you only see 2 lines. For lithium, you see 4 lines. And then helium, you can see the 1, 2, 3, 4, 5, 6, 7, 8 lines. So they are very unique for each element. So therefore, we can use the light spectrum to identify the elements using their atomic fingerprints. So this is a demonstration of a continuous spectrum of white light and the emission spectra of mercury, nitrogen, neon, hydrogen, image through a diffraction gradient. So if you watch it YouTube, it's a good, very nice YouTube to watch. So I recommend you to watch it. Now, when you see the light, it's because the electron moving around from lower energy to higher energy level. All of these are built based on the Bohr model of atom. So Niels Bohr, as scientist, he speculated that electrons orbit about the nucleus in a fixed energy level. He called orbit 1, orbit 2, and orbit 3. And electrons are found only in a specific energy level and nowhere else. And he said that electron energy levels are quantized. So he showed us evidence of for energy level. So he said that the electric charge temporarily assigns an electron to a higher orbit. When electron drop back down, a photons is given up. So let's say that one electron is excited from a level 2 to level 4. When it drops down to the lower energy level from go back to 4 to 3, it excited it will give up a photon. So the red line here is show the least energetic correspond to energy correspond to an electron dropping from energy level 3 to energy level 2, whereas for the violet line it corresponds to electron drop from energy level 5 to energy level 2. Now all of these are energy amount of energy. It do not correspond to number of electrons. Each of the number represent an energy level. It do not represent number of electrons. So if you had an electron drop from level 7 to level 3, it does not mean that it gives us 4 photons. It does not associate with 4 electrons either. For each electron drop from higher energy level to the lower energy level, it gave up 1 photon. So if there are 4 electrons, then it gave up 4 photons. Now, within an energy level, they are divided to sublevels. These sublevels are given by the designation of S, P, D, and F. So these designations are in reference to the principal diffuse and the phi lines in the emission spectra. So the number of sublevel in each level is the same as the number of the main energy level. What I mean when I say that, the 1s energy level do not have sublevels, so we're not talk about 1s. But for the 2 energy level, it had 2 sublevel S and P, where the 3 energy level had 3 sublevels S, P, and D. So here, so 1s doesn't have it, but 2 and 3 have 2 energy level. How many electrons occupied in each sublevel? For the S sublevel, it can hold maximum of 2 electrons. A P can hold a maximum of 6 electrons. A D can hold a maximum of 10 electrons. And the F sublevel hold a maximum of 14 electrons. Now, the maximum of electron per level is obtained by adding the maximum number of electrons in each sublevel. Okay, let's look at some example here. Like I said, energy level 1 does not have any sublevel, so it holds a maximum of whatever the S sublevel is, which is 2 electrons. But for energy level 2, it has 2 sublevel S and P. S hold maximum of 2, P hold a maximum of 6 electrons, so the total maximum electron that the 2 energy level 2 holds is 8 electron. For energy level 3, it has 2 sublevels, S, P, and D. So S holds 2 electrons, P holds 6 electrons, D holds 10 electrons. So it can hold a maximum 18 electrons. Likewise, for energy level 4, it can hold maximum 32 electrons because it have extra energy level F, would hold a maximum of 14 electrons. Now, electrons do not arrange randomly in the nucleus. It's arranged in a regular manner. So the first electron will feel the energy sublevel closer to the nucleus, and then continue to fill in its sublevel until it's full. A partial lift of sublevel in order to increase in energy, as shown here, start from 1s, go next to 2s, 2p, and so on. But you can look at the figure, it can show you better. You can see in the y-axis is increase in energy. So 1s is the lowest energy, while 6s the higher energy. Now notice that electrons don't come in the field in 1, 2, 3, 4, 5s. They come from 1s, they go to 2s, then they go to 2p, 3s, 3p, 4s, and so on. Or you can see it from the periodic table. Start with 1s for hydrogen, then 2s for lithium and beryllium, 2p for all of the elements, and 3s for the element, and so on. You can put electrons into a electron configuration. So the electron configuration is the shorthand method of writing the location of electron by sublevel. And it is written followed by subscript with the number of electrons in the sublevel. For example, 2p sublevel contains 2 electrons is written at 2p2, and the electron sublevel are arranged according to increase in energy as shown in the previous figure. So let's look at example for bromine. First, you determine how many electrons are in the atom. Bromine has 35 electrons. It has 35 electrons because atomic number 35, it has 35 protons, that means it has 35 electrons. So you arrange them in the energy sublevel according to increasing in energy, 1s, 2s, 2p, 2s. And you fill in the electron with the maximum number of electrons for each sublevel can hold. Like s only can hold 2, p only can hold s, and d only can hold 10. Then you sum all of the subscript equal to atomic number bromine or number of electrons. So you add all the superscript 2 plus 2 plus 6 plus 2 plus 6 plus 2 plus 10 plus 5. It gives you a total of 35, which is 35 electrons bromine has. So we will do some practice in the class, but let me we can stop here, and we can do some practice when I miss you in class.